I am Sheikh Rashidul Rahman, Assistant Professor, Department of Electrical and Electronic Engineering, University of Asia Pacific. So today I am going to deliver my lecture on the topic admittance or bus admittance matrix formation. So today we will learn how bus admittance matrix can be formed for a different power system network. So bus admittance matrix is a new conception for you, but the process to formulate this admittance matrix equation is same actually. It means that it's almost same from your conception of first year, first semester DC circuit, because to formulate the bus admittance matrix, we will use the nodal equation. So actually, what is the bus admittance matrix and how we can formulate this admittance matrix? So at first, we have to know that our power system is a interconnected system. Here there are several generators are connected together to produce the power, and here different buses are connected with different elements like a load or transformer or connection from generator to bus. So it's an interconnected power system where maybe a single bus connected to 2, 3 or more than 4 line actually. So for this interconnected power system, whenever we want to calculate the power flow through this transmission line or through this network, we have to know the bus voltage of every single bus actually. We have to know the equation of current flowing from one bus to another or from generator to other buses. So to identify these equations or to calculate these values actually, we need to formulate the bus admittance matrix or Y bus matrix. So if we want to go through this new lecture actually, so at first to formulate the bus admittance matrix, we need to find out the nodal equation. So to identify the nodal equation, here we consider a simple network where there are two nodes actually. So two node means two connecting point. So first node, that is the M node, and second node, that is the N node. So there are two nodes, one is M and other one is N. And from these two nodes, there is a connected line or transmission line, which impedance is ZA actually, and the admittance YA is equal to inverse of ZA. So here there is a current, that is IM, that is entering the M node, and there is another current IN that is entering in N node. Here there is a voltage difference from reference bus to M node or M point or M bus, that is the VM, and the voltage difference from N node or N bus to the reference is Vn. So if this is only one branch actually, because this impedance ZA consists a single series branch actually, and the voltage difference of this branch is VA. So this is VA is the voltage drop between M to N node. This is the voltage drop VA across to the admittance or impedance ZA, which is the actually the voltage difference between two nodes M to N. Now, so if actually the current entering from M node, that is IM, and if we consider this current is equal to IA, it means that this current IA is the series branch current. Then IN should be minus IA, because here the current is entering through the M node. So whenever we consider the N node, this entering current is the same direction, that is the current entering to the N node, but with respect to M that should be negative. So IN is equal to minus IA. So If we consider the n node current, then with respect to m node, this current should be negative direction. So In is equal to minus Ia. But Ia is same because this is a only series branch, so current should be the same. So there are two current actually, two nodes. So we can write down this equation in a matrix form. So how we can write down this equation in a matrix form? So at first, in the left side of our matrix, we have to write down the equations, left side value of the equation. That is Im, that is the first equation. So here Im. Next In is the second equation. So there is a second row, that is In. So these two row means that there are two separate equations. So first row is represent the first equation element, second row is represent the second equation element. So these Im and In is equal to, here the right side of the equation, that is the variable Ia, and here this is the same variable Ia. So there should be a single variable Ia. Now the coefficient of Ia in the first equation is 1, so that is 1. And now in second equation, the coefficient of Ia is -1, so that is -1. So this one is from m node, and these -1 come from n node actually. So this is at the first equation, or equation number 1 actually. So now for this equation, we can find these two Im and In current equations for these two different nodes. Now in equation 1 is being formulated in a matrix format actually. So the voltage drop of this series branch VA should be equal to, voltage means current into admittance, or current divided by impedance actually. So voltage VA means, VA is the potential difference between two nodes, that is M and N, these two nodes, that is the VA. So VA means actually Vm minus Vn. So VA means Vm minus Vn. So potential difference between two nodes. So we can write down this equation, VA is equal to Vm minus Vn in a matrix form in equation number 2. So this is a single equation. So left side in the matrix, there should be a single value, that is VA, because this row represent the equation. There is a single equation. Now there are two variables in the same equation, that is Vm and Vn. So if there are two variables, we can write down this in a column format. So Vm, Vn. And now in the left side of the column of this voltage equation, we have to put the coefficient. So the coefficient of Vm is 1 and coefficient of Vn is -1. So we have to put this +1 and -1. This +1 represent M node and this -1 represent the N node. Because we know that is the formula of matrix multiplication, that is row into column. So that's why in the right portion is column and the left portion is the row. So now, because this is a single equation actually, so if now, so multiplying by ya actually, so if we multiplying the ya by the both side of equation 2, then from voltage equation we can find out the current equation, because voltage into admittance means current. So if we multiply ya in the both equation of equation number 2, we will get equation of ia, because va into ya means ia. So in the left side, that should be current equation ia, and that is the admittance ya from equation 3. Now multiplying the both side of equation 3 by the column vector of equation 1. So the column vector of equation 1. So the column vector of equation 1, that is the 1 or -1. So if we multiply +1 and -1 from the both side of equation 3, then we can find out that is the plus ia means Im and minus ia means in. So that is the Im and in. So Im and in is equal to, so that is the column vector 1 minus 1, that is ya, +1 -1 Vm Vn. So if we multiply this right side of equation 4, we will finally get the equation in this value, that is the ya minus ya plus ya into Vm by Vn. So this is the nodal admittance equation for branch ya, and the coefficient matrix is the nodal admittance matrix. So here actually from equation 5 we can see that in our circuit or in our diagram, there are two buses or two nodes. One is M and another one is N. So there are two buses or two nodes, and for two buses there are two current. One is Im and another one is In. So whenever we formulate the equation, that is the nodal equation or current equation for two different buses or for two different nodes, there should be two different current, and that is Im and In. So there are two different current, and current is equal to voltage into admittance or admittance into voltage. So there are two node and there are two voltage, that is Vm and Vn, and the left side of the matrix of the voltage matrix, the left portion of the voltage matrix, that is called the coefficient of voltage, and the coefficient of voltage is y and the minus y and minus y y. So this is a 2 by 2 matrix, because whenever there are two equations or very left side of the matrix, there are two row, then that should be 2 by 2 matrix actually. So the coefficient of voltage, that should be 2 by 2 matrix. So here there are 2 by 2 matrix, and these matrix, if we consider, then this matrix contains only admittance, nothing else. So this matrix contain only admittance of the network, nothing else. So this matrix is called the bus admittance matrix or Y bus matrix, because this matrix contain only admittance, nothing else. So that's why this is called the bus admittance matrix or the Y bus matrix. So now, if we consider that N is the reference node, or N is the node which voltage is 0, then Vn should be 0. So if Vn should be 0, then the current In should be 0. So this 2 by 2 matrix is reduced from 1 by 1 matrix. So finally, the equation should be Im is equal to only one admittance, that is Ya, and only one voltage, that is Vm. So if we consider that is the N node is the reference node and the voltage of N node is equal to 0, then Vn should be eliminated, and here the current In should be eliminated. So only one bus or only one equation should be present in this equation, that is the Im, and that is equal to the single node voltage Vm with the single admittance Ya. So this is the nodal equation for a simple series circuit actually, or simple two bus network. That is, the one is reference and another one is actually the main bus. So if we consider the nodal equation for a little bit larger network actually from the previous one. So in this equation actually, in this diagram actually, there are four buses. There are four buses and there are three generators. So at first, this is the generator 1, this is generator 3, and this is generator 2. So it is very important to consider the bus number as it is. Like here, this is the bus number 1, and for the next, this is bus number 3, and here, this is bus number 2, and the right side, this is bus number 4. So it is very important to consider the bus number as it is, that is 1, 3, 2, 4. If we want to consider or rename or renumber this bus, that is 1, 2, 3, and then 4, then we should relocate the connection also, because here there is bus number 3, and from bus number 3 there are 4 connections. One is to bus 4, another one is bus 2, another one is bus 1, and another one is to the generator. So from bus 3 there are 4 connections. If we mark it as bus 2, then bus 2 there are 4 connections, but in real picture bus 2 contains 3 connections. There are no connection between bus 1 to bus 2. So if we want to relocate the bus number, we have to rearrange the connection as well as. It means that if we want to put here bus number 2, then the connection should be changed, because from bus 2 there should be 3 connection. So we have to maintain the 3 connection here if we want to renumber the buses. And if we put the 3 here, then we have to put 4 connection here. So if we want to renumber the bus, we have to relocate the connection as well as to satisfy the basic diagram of the power system. So this is a very basic thing, and I know that we all learn this in our first year, first semester. So if we consider the bus number as it is, that is 1, 3, 2, and 4, then there are 3 generators, that is the EA, the voltage source of generator 1 connected to bus 1, the voltage source of generator 3 connected to bus 3, voltage source of generator 2 connected to bus 2. And all these voltage sources are connected through an impedance actually, that is the ZA, ZC, and ZB. And this 0 is not a bus number actually, this is a reference bus. So the ground level or the reference level, we don't consider this as a bus. So this 0, we will not consider this as a bus. This is a reference bus, or this is the ground bus actually. And here this is another bus, that is the 4, and this bus there are no connecting generator or load. So this is a bus without any generator. And this is the connecting impedance from bus to other bus, that is bus 1 to bus 4, the impedance is ZD, bus 3 to bus 4 ZE, bus 2 to bus 4 that is ZH, bus 3 to bus 1 ZF, and bus 3 to bus 2 that is ZZ. Now we have to formulate the bus admittance matrix. We have to formulate the bus admittance matrix. For that reason, we have to convert this impedance diagram to an admittance diagram. So we have to convert this impedance diagram to an admittance diagram. So here, whenever we convert this, then this voltage source is converted to current source, and this series impedance will convert it to parallel admittance, because this is a basic source conversion. We already know the equation of source conversion, or how we can convert the source. So whenever you convert the source, voltage source should be converted to current source, and the series impedance of the voltage source will be converted to parallel admittance of the current source. So that is EA is converted to I1, that is the current source of bus 1, and ZA, that is the series impedance of the generator 1 or voltage source EA, now converted to parallel branch admittance, that is YA. So what is the equation of YA actually? YA is equal to inverse of ZA, or 1 by ZA. So similarly, ZC is converted to YC, and that is the inverse of YC. ZB is converted to YB, and that is the inverse of YB. So all other impedance of the other connecting buses are now converted to admittance. So that is the ZD is converted to YD. So ZE is converted to YE, and so others. So this is the admittance diagram. Now from this diagram, we have to find out the nodal equation. So whenever we have to find out the nodal equation, we have to apply the Kirchhoff's current law at every node. We have to apply the Kirchhoff's current law. So whenever, at first we have to apply the Kirchhoff's current law at bus 1. So whenever we apply the Kirchhoff's current law at bus 1, the basic equation is the sum of entering current should be equal to sum of the leaving current. So this is the Kirchhoff's current law actually. So here the sum of entering current, there is a single current entering to bus 1, that is the I1. So here I1 is equal to sum of leaving current. So there are 3 parallel branches. One is connected from bus 1 to bus 4, another one is bus 1 to bus 3, and another one is bus 1 to ground. So there are 3 parallel branches. So here current can be lived through these 3 branches. So sum of these 3 branches current equation should be equal to the sum of entering current, or I1. So here these 3 equations, at first if we consider the current passes through the admittance to the reference bus, that is into the YA, then the current equation of this branch should be voltage into admittance. So we have to assume the bus voltage, because in our question there is nothing mentioned about the bus voltage. So we have to assume the bus voltage. Here the bus number is a numeric value, that is 1324. So we can assume the bus voltage uh, with the match of this bus number. That is, for bus 1, we can assume the bus voltage is V1. For bus 3, we can assume the bus voltage is V3. For bus 2, we can assume the bus voltage is V2. And for bus 4, we can assume the bus voltage is V4. So we can assume this bus voltage actually. So here, now, so for bus 1, the bus voltage is V1. And now the equation of current through passes from bus 1 to ground, that is the V1 into admittance YA. So that is the V1 into admittance YA, plus the another current passes from bus 1 to bus 3, because there is a branch or there is a connection. So here, whenever we consider the nodal equation of a particular bus, then we have to consider this voltage is a positive voltage, because whenever we consider bus 1 voltage is a positive voltage or the greater voltage compared to other buses, then the current should be passes from bus 1 to other buses. So that's why whenever we apply the nodal equation for a particular point, we have to consider the voltage of this point is bigger compared to other node voltage. So V1 minus V3 into YF. So V1 minus V3 into YF, that is the current equation from bus 1 to bus 3. And another equation from bus 1 to bus 4, or current passes from bus 1 to bus 4, that is the V1 minus V4 into YD. So V1 minus V4 into YD. So this is the current equation that is passes from bus 1 to bus 4. Now if we just find out the coefficient of bus voltages, then we have to consider the V1, and the coefficient of V1 is YA plus YF plus YD. And there is no bus voltage at point at bus 2, because there is no connection between bus 1 to bus 2. So that's why there is no current passes from bus 1 to bus 2 directly. So that's why there is no bus voltage of bus 2. So the coefficient of V2 should be 0, because in the above equation V2 is absent. So the coefficient of V2 should be 0. And why the V2 is absent? Because there is no connection from bus 1 to bus 2. Now the coefficient of V3 should be minus YF, and coefficient of V4 should be minus YD. So this is equation number 1, or this is the nodal equation for bus 1. For similar way, we can find out the nodal equation for bus 2. This is the bus 2 actually. So if we consider the nodal equation for bus 2, then entering current should be I2 and is equal to the leaving current. And leaving current here, the bus voltage is V2, so V2 into YB. And next, from V2 to V3, that is V2 minus V3 into YG. And finally, V2 minus V4 into YH. And here we can rearrange the equation and find out the coefficient of bus voltages. That is, there is V1 absent because there are no connection between bus 2 to bus 1. So there is no point to place here in V1. So the coefficient of V1 is 0, and the coefficient of V2 should be YB plus YG plus YH, and coefficient of V3 should be minus YG, and coefficient of V4 should be minus YG. So this is equation number 2, or this is the second nodal equation. And here, for similar way, we can find out the nodal equation of bus 3, and we can find out the nodal equation of bus 4. And this is the 4 nodal equation. So now, if we want to consider this nodal equation to place in a matrix form, because we have to determine the bus admittance matrix. So we have to determine a matrix. So that's why we have to put down the equation in a matrix form. So that's the reason we have to put this 4 equation in a matrix form. So if we want to formulate a matrix, the conception is very simple. There are 4 equations. So the left side of the matrix contains 4 rows. So that is the 4 row. First row I1, I2, I3, I4 is equal to, there are 4 variable actually, that is the bus voltage. 4 buses, there are 4 bus voltage. So very right side there should be a 4 row, that is the V1, V2, V3, V4, and before this matrix there should be the coefficient of bus voltages. And we know the matrix multiplication rules, that is the row is multiplication with the column. So row element with multiply with the column element. So that's why, and very first row of the coefficient matrix there should be in equation number 1, that is I1. So in equation number 1, the coefficient of V1 is YA, YF and YD. So YA plus YF plus YD. So here YA plus YF plus YD. Now the second element of the first row of the coefficient matrix should be in the first equation, that is in the equation of I1, the coefficient of V2. So the coefficient of V2 is 0. So here there should be a 0. Now the third element of first row should be the coefficient of V3 in the equation of I1. So in the equation of I1, the coefficient of V3 is minus y. So there should be minus y. Now the fourth element of first row of the coefficient matrix should be in the equation of I1, the coefficient of V4. So in the equation of I1, the coefficient of V4. So in the equation of I1, the coefficient of V4 is minus YD. So here there should be minus YD. So this is how we can formulate the matrix from the equation actually. So this is the equation number 1 or I1. So this coefficient row contain the coefficient of bus voltages in the equation of I1. So this is I2 actually. So this is the equation of I2. So that's why the second row of the coefficient matrix should contain the coefficient of bus voltages in the equation of I2. Similarly for later 2 actually, 2 buses. So whenever we formulate this equation, then this is the coefficient matrix equation. This is the nodal equation, or this is the current equation. This is the coefficient matrix equation, and this is the bus voltage equation. Now, if there is a given power system network, and in a question you have to determine the nodal equation, then the answer should be up to this. That is the equation number 4. So these 4 are the nodal equation. So answer should be up to this. If your question you have asked to write down the nodal equation in a matrix form, then you have to write down the nodal equation in the matrix form or up to this point, up to this. Now, if your question you have to ask to find out the bus admittance matrix, then from these actually you have to determine the bus admittance matrix. You have to determine the bus admittance matrix. So how we can formulate the bus admittance matrix? So we know this is the coefficient matrix of bus voltages of separate current equations, actually bus current equation, and this coefficient contains only admittance, and these admittance are the network admittance. Network admittance means the admittance value which is given in the question or in the figure. So this is the network admittance. Now from this network admittance we can formulate the bus admittance matrix, and here this matrix is called the bus admittance matrix. Here every y should be capital Y. So this y is not a small y, this is the capital Y. So that should be capital Y. So whenever we write down in a matrix with capital Y format, then we can consider this is as a bus admittance matrix, because this matrix contains only admittance. So that's the reason this is called bus admittance matrix. So this is the bus admittance matrix. So in short form, this can be written as capital Y suffix BUS, bus, capital Y suffix bus. That is bus admittance matrix. So we can write down this is a short form of bus admittance matrix. So here, capital Y11. Here there are two meanings. Actually, there are two meanings of this notation. That is capital Y11. The first meaning of this notation is this is the first row, first column element of the bus admittance matrix. So this is the first row, first column element. So similarly, Y12, it means that this is the first row, second column element of the bus admittance matrix. Y43, it means that this is the fourth row, third column element of the bus admittance matrix. This is the first meaning. There is another meaning actually. So which is the another meaning? That is the Y43. It means that this is the admittance value of connected bus from 4 to 3. This is the another meaning. That is Y43 means this is the admittance value from connected bus 4 to 3. That is the Y14. What is the meaning of Y14? Y14 means this is the admittance value of connected bus 1 to 4. 1 to 4. So this is the meaning. So in this bus admittance matrix, we can divide this element in two separate categories. This bus admittance matrix element, we can categorize this in two separate categories. At first, that is the mutual admittance, and next, this is the self-admittance. So whenever that is the Y11, Y22, Y33, Y44, that is called self-admittance of this bus. So self-admittance, whenever we find out the same row and same column, this element called the self-admittance. So here there are self-admittance in every row. There should be a single self-admittance. That is the first row, there is a self-admittance, that is Y11. In second row, there is another self-admittance, that is Y22. In third row, there is another self-admittance, that is Y33. In fourth row, there is another self-admittance, that is Y44. So every row, there should be a single self-admittance. So these are the diagonal elements. So these are the diagonal elements. So the self-admittance of the Y bus are the diagonal elements. So the self-admittances of the Y bus is a diagonal element actually. So Y11, Y22, Y33, Y44, these are the diagonal elements. So these are called the self-admittance. And the off-diagonal elements are called the mutual admittance, the off-diagonal element. So if we just cross this diagonal, then this is the upper off-diagonal element like Y14, and this is the lower off-diagonal element, that is the Y41 or Y42. So these upper and lower off-diagonal elements are called the mutual admittance. That is the Y12, 13, 14 or 42 or 34. That's all are the call of mutual admittance. So now, what is the meaning of mutual admittance and what is the meaning of self-admittance? So Y14 is the mutual admittance, and it means that this is the admittance value of connected bus from 1 to bus 4. So this is the mutual admittance. So if we consider the diagram, that is the value of Y14 is minus YD. And if we consider the diagram, that is this YD is the mutual admittance, or this YD is the admittance connected from bus 1 to bus 4. This is the connecting admittance from bus 1 to bus 4. So this is the Y14 mean mutual admittance or connected admittance from bus 1 to bus 4. And the self-admittance means the sum of all admittance connected to this particular bus. if we consider Y11, that is the self-admittance of bus 1, it means that the summation of all admittance connected to bus 1. So if we go through this diagram, then in this diagram, for bus 1, the connecting admittance to this bus 1 is YA, YF and YD. So if we want to calculate the self-admittance of this bus 1, it means that we have to sum up the all admittances connected to bus 1, that is YA plus YF plus YD. So that is YA plus YD plus YF. It means that the sum of all admittances connected to bus 1. So that is called self-admittance. Similarly, if we consider the Y33, then Y33 means the sum of all admittances connected to bus 3, that is YC plus YG plus YF plus YE. That is YF plus YE plus YC plus YG. So that is the Y33. So there are two types of admittances. One is the self-admittances, another one is the mutual admittances. So the self-admittance means the all admittance connected to a particular bus. This is the summation actually. So the sum of all admittance connected to a particular bus, this is the self-admittance of this particular bus. And mutual admittance means connecting admittance between two different buses, like Y23. It means that the mutual admittance between bus 2 to bus 3. It means that the connecting admittance between bus 2 to bus 3. Now, the value of self-admittance is negative and the value of mutual admittance is positive. So you don't think about these two lines right now, because if you want to think about this two line right now, maybe you will confused. Maybe you will be confused. So there is no need to think about this two line right now. You will understand the meaning of this two line whenever you just finish this lecture. Automatically you will understand these meanings. So now just ignoring this two line. So now another thing we want to know from this bus admittance matrix, that is the value of Y11 is equal to YA plus YD plus YF, and value of capital Y12 is equal to minus of YF. So what is the value of YF? We have to multiply with a minus 1 with this particular value, and then we will find the bus admittance matrix element Y12 value. So this is a simple difference between the element of bus admittance matrix and between the network admittance value. So that's why this is the small y and this is the capital Y, because the small y represent directly the network admittance value and capital Y represent the element of bus admittance matrix value. And here the mutual admittance for this bus admittance matrix element, that is Y14, should be the network admittance with multiplying by a minus 1. So this is the basic difference of network admittance value and the bus admittance matrix value. So if we want to consider a network admittance value to a bus admittance matrix value, we have to multiply a minus 1 with the network admittance value to find out the mutual admittance value of the bus admittance matrix. But for the self-admittance matrix value, we don't need to multiply a minus 1, because if we go back through Y11 equation, there should be YA plus YD plus YF. So there is no minus 1 multiplying with this value. So whenever you consider the self-admittance, we don't need to multiply a minus 1 with the network admittance value. But whenever we have to calculate a mutual admittance, we have to multiply a minus 1 with the network admittance value. So this is the another basic difference of the network admittance value and the bus admittance matrix value. So from here, we can consider some important decision actually regarding this bus admittance matrix. So if I will sum up this decision, then the first one, that is the bus admittance matrix, is the connected admittance matrix bus of a particular power system network. The dimension of bus admittance matrix should be follow the total number of bus of a particular power system. That is, here the bus total number of bus of this particular power system is 4. That is 1, 2, 3, 4. That is the 4. Total number of bus of this power system is 4. So that's why here the dimension of Y bus matrix should be 4 into 4 or 4 by 4. 4 row, 4 column. If in our particular power system diagram there are 6 buses, then our Y bus matrix dimension should be 6 by 6 or 6 into 6. That is 6 row and 6 column. If a power system contains 100 buses, it means that the dimension of Y bus should be 100 into 100. So 100 rows and 100 columns. So this is the decision number 1. Decision number 2. A Y bus matrix contains 2 types of admittance. One is self-admittance, another one is mutual admittance. The self-admittance means the summation of all admittances connected to a particular bus. If we want to say the self-admittance of bus 3, it means that the sum of all admittances connected to bus 3. And mutual admittance, for the mutual admittance, if we want to consider a mutual admittance, that is for an example Y2, 3, it means that this is a connected admittance between bus 2 to bus 3. This is the mutual admittance. The very interesting thing for mutual admittance is that if we consider the diagram bus 2 to bus 3, then the connecting admittance between bus 2 to bus 3 is YG. And if we want to consider the mutual admittance of bus 3 to, it means that the connecting admittance from bus 3 to bus 2, then there should be the same admittance, that is the YG. Because these admittance is connected from bus 2 to 3 and bus 3 to 2. The connecting line admittance is same. So the interesting thing for mutual admittance is the upper diagonal mutual admittance should be same of the lower diagonal mutual admittance. It means that if we shift a row column of a mutual admittance, the value doesn't shift, value will remain same. So if we shift the row column of this mutual admittance, it means that instead of Y14, if we consider Y41, that is the 4th row first column element Y41, the value should be same as value Y14. So the value of Y14 is minus YD. So the value of Y41 should be minus YD, and that is minus YD. Because the mutual admittance is same. Because if we consider bus 3 to 1, the value of admittance, and if we consider bus 2 to 3, the value of admittance should be same. So that's the reason the upper diagonal and lower diagonal mutual admittance should be same. So if Y12, the value of Y12 is 0, it means that the value of Y21 should be 0. If we find out the value of Y23 is minus YG, then value of 32 should be minus YG. So the upper diagonal and lower diagonal element should be same. So if we shift a row to column and column to row of a mutual admittance, the value should be remain same. So this is a very interesting thing for mutual admittance. So this is the decision number 2nd. And the third decision is very much interesting decision, and that is the bus admittance matrix element should be capital Y and the network admittance matrix should be small y. And whenever we want to calculate the bus admittance matrix of self-admittance, then there should be the sum of all admittances connected to a particular bus. But whenever we want to calculate the mutual admittance, we have to multiply a -1 with the value of network admittance. We have to multiply a -1 with the value of network admittance. And how this -1 is comes in the equation, here we just derive the equation, and from nodal equation this -1 is come. So from the nodal equation we found this -1, which is in the multiplying condition with the value of network admittance. So this is how we can calculate the self admittance and mutual admittance for a particular power system. So this is called the bus admittance matrix, and this bus admittance matrix is very much important for it to calculate the power flow equation of interconnected buses, because whenever we want to calculate the value of I1, we have to know this Y bus matrix, because if we don't know this Y bus matrix, we will not able to calculate the network current or the power flow of the network. Because without approaching this method, if we want to calculate the power flow equation of a power system, there should be very much difficult approach, because here you see this particular bus connected with 2 or 3 other buses. So this is an interconnected system. So whenever this connection is considerably huge, there is a 50, 100 or 150 buses or 30, 40, 50 buses in a power system. So this is a clumsy of connection actually. So if we want to consider the power flow equation of this particular power system network, we have to follow the equation in a matrix format to find out the power flow equation. So that's why the bus admittance matrix is very much important in power system network calculation. Whenever we consider the power system of 2 buses or 3 buses or like 4 buses, you may think that without formulate this bus admittance matrix, we can easily calculate from the nodal equation to our actually the current, or we can determine the power flow of the different buses. But whenever the power system is considerably large, like 30, 40, 50 or more than 100 buses in a particular power system, this time this is so much difficult to calculate the power flow solution by using the separate nodal equation of every buses. So we have to formulate the all equation in a matrix form, and from this matrix we have to calculate the bus admittance matrix. And whenever we can do this, our power flow solution becomes easier to achieve. So that's why bus admittance matrix is so much important in power system calculation. And you have to study this bus admittance matrix formulation very actually well. So you have to consider this topic as an important topic, and you have to study this with a full attention to identify how we can calculate or how we can formulate a bus admittance matrix for a particular power system. So this the first part of my lecture of how we can formulate the bus admittance matrix, and in my second part actually we formulate the bus admittance matrix with numeric value. So that's all of the first part of my lecture. Thanks to all to listen.